I'm the director of the Energy Systems program here at Lehigh University. And welcome to our Energy Systems Engineering seminar series for the spring semester. And this is the fourth in the series. And I'm really very proud and honored to have uh, Laura Marsiglio be the presenter. The title of the presentation is Future of Electricity Strategies for Tackling the Energy Trilemma in New York. And Laura is an analyst with National Grid and the Future of the Electric team. She works with several other stakeholders to develop strategic plans to facilitate the transition to clean energy. Her focus is on initiatives that will drive operational and capital efficiency in the New York electricity business. Prior to joining National Grid, she earned a BS in Integrated Engineering and Social Science from Lehigh University's IDEAS programs, studying materials engineering, economics, and environmental policy. Laura also earned a Master of Engineering in Energy Systems Engineering, and so she was one of our students 4 or 5 years ago. I'm really proud to have her back here making this presentation. So Laura, just to go through some quick housekeeping items. Laura will talk for roughly 45 or 60 minutes, and then we'll open the floor for Q&A. And as before, we first of all entertain questions from the students, then I'll open it up to the general audience. So Laura, welcome back to Lehigh, and the floor is yours.
Thank you. Let me share my screen here. Can you see that okay?
Looks good.
Okay, perfect. Well, good afternoon, everyone. Thank you, Dr. Shankar, for such a kind introduction and for inviting me back to speak again this year. As he mentioned, I work for National Grid as an analyst on our Future of Electric Strategy team in New York. So my team's focus is on developing a strategy that allows the business to meet regulatory requirements as well as the needs of customers. So I spent a lot of time thinking about and talking about current challenges that the industry is facing and strategies for addressing those challenges. So my presentation today is going to be about exactly that. What does the energy landscape in New York look like right now? What are the challenges and what solutions exist for utilities to tackle those challenges? So the first question, what does the energy landscape in New York look like right now? I pulled some media headlines. Although they're often sensationalized, they can give us some idea of kind of the current state of affairs. So over the summer, the New York State Energy Research and Development Authority, or NYSERDA, along with the Department of Public Service, released a draft report that showed their base case analysis found that the state would likely be delayed in hitting its goal to generate 70% of electricity from renewable sources by 2030. Shortly after that top article was published, which announced that an audit found that the Public Service Commission hadn't done enough to help the state reach its clean energy goals. In the fall, the New York Independent System Operator, NYSO, identified a potential shortfall in capacity for New York City, which prompted the next headline, drawing attention to the risks that growing peak demand can pose for reliability. And then just last month, the governor announced that she would be taking action to address utility bills, which was prompted by a recent rate filing from Con Edison. Now, I chose the most critical headlines that I could find in order to make a point, because you almost get whiplash from reading these next to one another. But every single one of these things is important. New York set ambitious decarbonization goals because the potential impacts of unchecked global warming are severe. Maintaining reliability of the grid is essential because our society has really become dependent on the 24/7 availability of electricity. And affordability is important because costs everywhere seem to be rising right now, and people shouldn't be burdened by the cost of energy. So this is the energy trilemma. Energy has to be reliable and affordable, but it also has to be sustainable. As the headlines in the last slide illustrated, it can be challenging to do all of three of these things at once. Strategies necessitate trade-offs, so I'll be using the energy trilemma as a framework to talk about the challenges that are associated with decarbonizing the electric grid in New York, as well as some of the potential solutions. Before we dive in, I just want to remind you all of the role that utilities are able to play in the energy transition. So in New York, electricity markets were deregulated in the late 1990s with the goal of increasing competition and lowering prices. As a result, utilities had to divest from their generating assets, and they're still prohibited from owning generation facilities with a really small number of limited exceptions. So when we talk about utility strategies for enabling the clean energy transition, the focus is largely on interconnecting new generation to the grid and ensuring reliability as that electricity is delivered to customers. I think this visual provides a cool view as to what the future of electricity might look like, the future of the grid. And I'll talk a little bit about generation today, largely in the context of interconnections, but a lot of the solutions that I'm going to talk about will be focused on the transmission and distribution system. So we'll start by taking a look at what sustainable energy means for New York. Sustainable can mean a lot of things, but typically the conversation focuses on increasing generation from renewable sources. The carbon reduction potential of electrification efforts is dependent on the carbon intensity of generation. So economy-wide decarbonization goals are tied directly to a sustainable grid mix. So in New York, economy-wide decarbonization goals were set by the Climate Leadership and Community Protection Act. The CLCPA was signed into law in July of 2019, and it lays out a series of interim goals with the ultimate objective being to reduce economy-wide emissions 85% by 2050. So decarbonization is primarily accomplished via two means, energy efficiency and fuel switching. So we can use less energy or we can use cleaner energy, but ideally we do both. So let's take a look at progress against these goals a little over 5 years since they were set. In October of this last year, NYSERDA announced that the state actually hit its goal to interconnect 6 gigawatts of distributed solar. So they hit it a little bit early before the 2025 deadline. But in order to reach a grid mix that's comprised of 70% renewable energy by 2030, a lot of progress has to be made. So much of the renewable capacity shown in this chart is denoted as being in the pipeline, which means that the projects are not yet operational and are likely in some phase of the interconnection process. This is important because according to a study by Lawrence Berkeley National Lab, the total time from interconnection request to commercial operation date averaged about 5 years in NYSO territory from 2018 to 2023. Said in a slightly different way, in order for the state to meet the distributed solar, energy storage, and offshore wind goals for 2030, over 5 gigawatts of energy storage and 7 gigawatts of offshore wind should probably be entering the queue this year. But the challenge here is that there's already a significant amount of capacity in the interconnection queue. This chart shows the total active capacity in interconnection queues across the country over the past 10 years. And I think it makes it clear that capacity in queues has grown significantly in the last decade. But in order for the decarbonization potential of these renewable resources to be realized, they have to be connected to the grid. They can't be stuck in the queue. So there are efforts underway to address the backlog of capacity that's stuck in the interconnection queue. In July of 2023, the Federal Energy Regulatory Commission issued Order 2023, which included a number of reforms that are reforms to the interconnection process that are intended to address these backlogs. I think the most notable was the requirement that transmission providers study projects in clusters. So traditionally, interconnection queues were just that, a queue or a line. So the first project to file an interconnection application was the first to undergo studies. As you can imagine, this is a pretty time-intensive approach to go one by one, but the new cluster study process requires utilities to group interconnection requests to study them. So instead of going one by one, they're looking at all of the projects that will impact, let's say, one substation at a time. And the added benefit here for developers is that the cost of any necessary grid upgrades will be split. So it'll be split using a proportional impact method, but this means that all of the developers in that cluster have the opportunity to share the cost of upgrades that they're all going to be benefiting from. FERC Order 2023 also aimed to reduce the number of projects that drop out of the queue once they're entered. So this is important because if a project enters the queue and the utility is spending time doing a study to understand the feasibility and what it would cost to interconnect, and then it turns out that the project is over budget or off schedule, and it drops out of the queue, then all of that time was spent on a project that is never going to be operational. So FERC Order 2023 has 4 stipulations to try to reduce the occurrence of this. So the first is increasing the amount that developers have to pay as a deposit to the utility that's carrying out the study. Developers are also required to prove that they have the right to occupy or develop the site before they enter the queue. They're also required to submit a commercial readiness deposit. And then lastly, the utility is now required to impose a penalty if the developer withdraws from the interconnection queue. And that penalty is based on time spent on doing a study so far and impacts to other projects that are in the queue. So these controls serve to ensure that projects entering the queue are actually viable and deter developers from submitting interconnection requests for projects that might not actually be built. Utilities are also working to make improvements to their end of the interconnection process. So a couple of the ways that's happening, better internal data governance can improve the efficiency of interconnection studies. Transparency and accountability will help to improve relationships with developers and provide them with more insight into project schedules and milestones. And then lastly, better training for developers will enhance the ease with which they're able to interact with the tools that are provided by the utility to facilitate the interconnection process. Some of these changes are still relatively new, so it's going to take some time before utilities and developers see the full impact of the improvements, but it's important that the change is underway. Now I want to talk about another component of the CLCPA, which is the requirement that 100% of light-duty vehicle sales be zero-emission vehicles by 2035. As far as I know, there's not a regulatory mechanism in place yet to ensure compliance with this, but I added this chart to talk about how even though the state might set targets or make laws, it's ultimately customer adoption that's going to determine when upgrades to the grid are required. So the top line here is the policy scenario from NYSO's 2024 Gold Book, and it shows the forecasted percentage of light-duty EVs in the state if that policy target is achieved. So the assumption here is that EVs make up 100% of sales share for passenger vehicles starting in 2035. The second line in blue is the baseline forecast from NYSO's 2024 Gold Book, and they're assuming for this scenario that only 85% of light-duty vehicle sales in 2035 are EVs. And this baseline scenario is what NYSO expects load to look like in their territory. So they're basically planning for EV adoption to lag policy targets. So let's talk about why this is so important. I mentioned that in a strategy, there are trade-offs. Utilities and the ISO have to forecast how customer demand is going to change so that they know when and where to make upgrades to the grid. So if utilities just looked at the state's policy goals, they might end up investing in grid upgrades too early. And those upgrades are customer dollars that could have been spent elsewhere. So that's why this recognition of a delta between policy targets and forecasted customer behavior is important. I also want to show you this chart to illustrate how customer adoption of electric vehicles on the last slide translates to an impact on peak demand. So you can see it's a pretty steep line. So this chart is the reason that grid upgrades will be required as customer adoption of EVs grows. Okay, so we talked about sustainability. The main challenge here is interconnecting renewable resources to the grid quickly enough to meet decarbonization goals set by the state, while also keeping pace with increased customer demand. And now I want to talk about why that matters for reliability. So we just looked at that chart showing the impact that EVs are going to have on peak demand. There are also other factors that are driving an increase in peak demand. This is things like heat pumps, electric appliances, and large loads. The chart on the left here shows the total forecasted increase in peak demand for New York for NYSO territory. The lower demand scenario shows an increase of around 10 gigawatts in peak by 2054. But the high demand scenario shows that peak demand could double over the next 3 decades. So that's pretty crazy. I also showed you all of the capacity that's in the interconnection queue right now, but it turns out that retirements of traditional generating facilities have outpaced the addition of new capacity over the past couple years. This is another reason why it's important that projects are able to move quickly through the interconnection queue. The addition of renewable energy has to keep pace with state policy targets, customer demand, and the planned retirement of power plants. This matters because one factor that can impact grid reliability is frequency. So the frequency of the grid is impacted largely by the balance of supply and demand. The grid operates at a frequency of 60 hertz, but once you start to deviate too far in either direction from that, equipment connected to the grid starts to trip offline. So that balance matters for reliability. This is another trade-off. While we want to increase the share of renewable energy connected to the grid, the total pie is getting bigger. So we're trying to interconnect as much renewable energy as we can, but we might not be able to retire natural gas plants if we need them to meet peak demand. So reliability is likely to be prioritized to an extent over sustainability in the near term. I mentioned that large loads are one of the drivers of an increase in peak demand in the state. And this map from NYSO shows some of the large projects that are looking to interconnect. And the time frame here is between 2024 and 2026. And if you add up the demand from these projects, it's just under 2 gigawatts, which is about 6% of what peak demand in New York was for 2023. So all of this new demand is coming online in just a couple years. So in order to meet this growing demand from customers, we have to ensure that we have an adequate supply of electricity. We also have to make sure that the physical grid infrastructure can handle that added capacity. And to do that, utilities across the state are building new transmission lines. One of the cooler projects, I think, is the Champlain Hudson Power Express. So this transmission line is going to deliver hydropower from Quebec to New York City and is expected to be in service by 2026. The reason that I think this is cool is because if you look at the carbon intensity of NISO zones in upstate New York, 70% of their electricity is currently coming from zero emission sources. But when you look at downstate New York, only 2% of electricity is from zero emission sources. So statewide, we're at about 28%, but the upstate downstate differential is pretty shocking. But hopefully this new transmission line will help. These large-scale transmission projects are also expensive. So the project I just talked about is expected to cost $6 billion in total. So we have another trade-off here. How do we manage affordability when grid upgrades necessary to ensure reliability cost billions of dollars and take several years to complete? One of the ways that we can address this is by using grid-enhancing technologies like advanced conductors and dynamic line rating. So advanced conductors leverage innovative materials to increase the capacity of transmission lines. Utilities can reconductor existing transmission towers with these advanced conductors, so there's no need to site and permit new right-of-ways and then construct new transmission towers. So this saves time and money while still increasing the total capacity of the transmission system. These advanced conductors can also withstand higher temperatures, so they sag less, which makes them safer and enhances reliability in that way as well. There are a few different methods for doing dynamic line rating. One uses LiDAR technology to monitor conductor sag in real time. So sensors mounted on the tower use LiDAR to look at current sag on the lines, but they also collect data about ambient weather conditions. And then this information can be used to adjust traditional static or seasonally adjusted line ratings based on the real-time conditions. Many transmission lines are able to safely handle more capacity, so using a dynamic line rating can help to alleviate congestion in critical areas of the grid. Dynamic line rating also allows utilities to optimize their existing infrastructure, which again defers or eliminates the need for costly and time-consuming transmission construction projects. DLR specifically can be installed relatively quickly and at a cost, a fraction of the cost of siting, permitting, and building a brand new line. So this is a cool solution because it improves reliability by increasing the capacity of existing infrastructure, but at a lower cost, which helps to maintain affordability. I want to circle back for a moment to the point that I made earlier about how the balance of supply and demand impacts grid reliability. So the chart that we're looking at here is the sum of all electricity supplied to the New York grid on July 7th of last year. And the data is at 5-minute intervals over the course of the day. So we know that supply has to equal demand. So this is also the demand curve for that day. July 7th was a Sunday, so weekend demand patterns are a little bit different, but we still see it pick up in the morning, increase throughout the day, and then peak at 7:40 in the evening. Now let's take a look at the supply curves for wind and other renewables on that same day. Other renewables should be largely solar, but obviously there are some other resources in there because overnight generation is still above 200 megawatts. We can see with the solar curve, the increase in supply in the morning as the sun comes out, relatively flat during the day, and then production drops off as the sun goes down. Wind supply, on the other hand, peaks a little bit after 1 a.m. and then falls really significantly in the early morning, where it remains below the other renewables curve for the rest of the day. This real-life example does a really good job of illustrating the challenge of increasing our reliance on renewable resources. So supply from wind and other renewables is at its lowest right before 9 p.m., but demand is still near its peak during that time. So as more of our electricity comes from renewable sources, it's going to be important to manage this delta. And now I'll show you what the generation mix looked like throughout the day to give you the full picture. So right now, what happens when solar and wind production drop off, natural gas and dual fuel plants ramp up in order to meet that peak demand in the evening. And remember, this peak is also expected to grow over time. So the challenge here is figuring out how to meet that peak with a generation mix largely comprised of zero emissions resources. That additional hydropower from Quebec that I mentioned will help with this. So you can see the curve for hydropower picks up with the natural gas curves to help meet peak on the grid. I think it's also interesting to note that nuclear generation is essentially a flat line. The difference between minimum and maximum supply for nuclear was only 18 megawatts on this day. And so even though nuclear is considered to be a zero emissions generating resource, the load following capability is limited. The efficiency of nuclear plants is optimized when they're running continuously at or near their capacity. So their ability to follow demand is limited. So this is a reason why improved battery technology is going to be increasingly important for managing reliability. Batteries can help to flatten the curve for solar and store energy during the day when demand isn't as high, and then dispatch it overnight to help meet that peak. This chart doesn't take into account behind the meter solar, so I just want to mention that quickly. If you've heard of the duck curve, it refers to the decrease in net load on the grid during midday hours, and then the associated significant increase in demand in the evening hours as solar production drops off and demand peaks. This is really prominent in California, but we're likely to see a similar phenomenon in New York as the amount of solar across the state increases. So again, that's an opportunity for battery technology to help manage the supply and demand balance. Okay, so I talked about reliability on a system level, at the transmission level, and some of the challenges that come with balancing supply and demand. And now I want to talk about reliability at the distribution level, at the customer level. So the New York Public Service Commission is the entity that's responsible for regulating utilities in the state. And as part of this responsibility, they set reliability standards for electric utilities. They also assess penalties if utilities don't meet these targets. So the PSC uses two metrics to assess reliability. The first is the System Average Interruption Frequency Index, or SAFE, and this is the average number of times that a customer is interrupted for 5 or more minutes during a year. SAFE performance can be impacted by the system design, the level of capital investment, the quality and frequency of maintenance on the system, and weather events. In 2023, the statewide SAFE performance was 0.58, excluding major storms. So outside of significant weather events, on average, customers across the state experienced less than one interruption in service throughout the year. And I think that's important because I think we sometimes take that for granted a little bit. I can't remember the last time that I had a power outage due to the grid. So, reliability is kind of something we take for granted, which is why it's important to make sure that, performance isn't impacted throughout the clean energy transition. So the second metric here is Customer Average Interruption Duration Index, or CAIDI, and that's the average duration or time in hours of the interruption for those customers that were interrupted during a year. So CAIDI can be impacted by workforce levels, management of that workforce, and geography. So especially in some more rural areas of upstate New York, parts of the grid might be harder to access. So that will impact how long it takes for a crew to get out there and address the fault and restore service. And then the statewide average KD performance in 2023 was a little under 2 hours. And this is again excluding major storms. So in this year, 2023, the three major causes of interruptions across the state, again excluding storms, were equipment failures, tree contacts, which I'll talk about later, and prearranged outages. So innovation can help to address reliability at the distribution at the customer level. FLISR, which stands for Fault Location, Isolation, and Service Restoration, is a grid technology that can improve reliability. I'm going to play this 30-second video for you because I think it makes the technology easier to understand. So I'll let this play. Okay, so basically, FLISR works by allowing reclosers to communicate with a central data concentrator, which uses pre-programmed logic to tell the feeder how to respond in the event of a fault. So if you saw originally when the fault occurred, the system was de-energized between recloser 1 and 3, but with the use of FLISR, customers between recloser 2 and 3 were able to be restored. So FLISR allows the fault to be isolated only to the impacted section of the network, while electricity is rerouted to customers that would have been otherwise impacted. At the same time, the control center is also notified when a fault occurs, which allows them to dispatch crews quickly if needed to respond. So as a result, fewer customers are impacted by a fault, which improves safety performance. The communication with the control center can also decrease the amount of time that it takes for a crew to respond, which improves KD performance. And then the information provided to the control center can also help them to more accurately assess how many crews might need to respond, where they need to be dispatched, and this can help bring down the cost of restoring those customers. So this is an instance where innovative solutions are improving both reliability and affordability. AMI, advanced meter infrastructure, smart meters, is another distribution system technology. So the new smart meters are able to send power out notifications directly to the control center, which eliminates reliance on customers to call their utility in order to report an outage. So this feature can help to reduce the duration of outages because the control center has greater visibility into the number of customers that are impacted as soon as they're impacted, which allows them to dispatch field crews more rapidly and effectively. Other benefits of smart meters, they can enable time of use pricing, which is again beneficial to both customers and the utility. If customers opt into the time of use tariff, they basically say that they're willing to shift their electricity use to off-peak hours. So they're charged different rates for using electricity on versus off-peak. So this is helpful. The customer can save money if they're able to successfully shift their usage. This also helps the utility by reducing peak demand, so can help to limit some of the necessary upgrades to the grid. Smart meters also provide hourly usage data, which customers can use to better understand how much electricity they use, when they're using it, and these insights can help them to improve energy efficiency. So at the start of this presentation, I mentioned that decarbonization happens in two ways: energy efficiency and fuel switching. AMI gives customers greater data visibility, which helps them to make decisions that can improve the energy efficiency of their home or business. The newest generation of smart meters, AMI 2.0, it's sometimes called, are also compatible with an app that customers can choose to download. And this app can integrate smart appliances. So one, this gives the customer greater visibility into how much a specific appliance is using, but the app will also let customers set timers. So this is helpful for that time of use pricing, because you can set a timer and have your dishwasher or your dryer run overnight. Okay, so now we've talked about reliability at the grid scale and at the customer level. And the primary challenge here is maintaining the balance of supply and demand. As demand due to electrification and large loads increases the system peak, we'll have to increase the total capacity of the grid. We also have to make sure that we have the right mix of generation resources to meet this peak. So lastly, I'll talk about affordability. I shared a headline at the start of my presentation in which the governor drew attention to utility bills. But when we talk about addressing challenges associated with sustainability and affordability, the bottom line is that more investment into the grid is going to be required. So how do we do it all? There are two ways that I think about addressing affordability. The first is by decreasing the total cost of utility work through operational and capital efficiencies. The second is by offering special programs and rates for low-income customers, as well as incentives for customers that are looking to invest in clean energy technologies. So before we really get into affordability, I want to talk about how a utility makes money. So the Public Service Commission is, in addition to being responsible for ensuring reliability, they're also responsible for setting utility rates, which is something that occurs during the rate case process. So the formal litigation of this process generally takes about 11 months to a year, but as you can imagine, it takes the utility just as long, if not longer, to prepare for the rate case. So this process is public and open. All rate case documents are published on the PSC's website, and members of the public, special interest groups, and other interested parties are able to participate in the rate-making process. So utilities earn recovery for their costs through the rates that are charged to customers. The revenue requirement, which you can see on the right, is used to calculate rates based on the number of customers and forecasted demand for the service territory over the course of the rate period. Rates are calculated. And then the revenue requirement, which again is determined during the rate case proceeding, is equal to the utility's operating expenses, like labor, plus capital expenses times a return on equity. So the return on equity is also negotiated during the rate case proceeding. And this number, that rate, is what determines the utility's profit. So operating expenses are a pass-through cost, and the utility only earns a profit on capital investments. And this is because New York has a revenue decoupling mechanism. So the revenue that the utility earns is not dependent on the quantity of electricity sold to customers. So utilities aren't making greater profits if, they sell more electricity. Okay, so when we think about how that translates to affordability for customers, Utilities can either decrease operational expenses or capital expenses. While recognizing that a significant capital investment is going to be required to build out the grid and facilitate the clean energy transition, there are ways that utilities can conduct work more efficiently to drive down unit costs. So operational efficiencies can come from process improvements that allow people to spend less time on a given task or engaging with a specific process. Better data availability and visibility can drive better decision making about where and when to invest time or money. And then digital tools are able to facilitate both of these improvements. Capital efficiencies can be driven by optimizing designs, so finding opportunities to tweak standard designs to reduce the cost of the design while still maintaining, of course, safety and performance. And then one of the big risks right now comes from supply chain instability. So costs for critical materials like steel, transformers, and conductors have increased over the past several years. We've also seen increased lead times, so the amount of time that it takes to receive materials once they're ordered. Again, for things like transformers and conductors, which are critical for grid upgrades, lead times have more than doubled in some cases. So one of the ways that we can combat this increase in costs and the risk to project schedule is by forecasting the materials that will be needed for projects well in advance of when they're actually needed, when we actually need them at a site. So this helps to mitigate budget and schedule risks. Digital tools are also can also help to provide capital savings by improving work methods and project management, facilitating better communication among teams, allowing people to get things done more efficiently. So I want to give you an example of how operational efficiency initiatives can be impactful, delivering savings for the company as well as benefits for the customer. So if we look at something like vegetation management, if you remember when we talked about reliability, I said that trees making contact with power lines were the second biggest cause of interruptions in New York in 2023. I'm not sure if the class, if you still read the case study about the 2003 blackout, but the cause of this blackout that impacted 50 million people is largely attributed to a tree making contact with a transmission line. So it's for this reason that utilities have vegetation management programs to regularly trim trees that are near power lines and remove hazard trees. So typically this is done on a time-based cycle. So based on an arborist's knowledge of regular growth rates in an area and observation of the infrastructure, a certain section of the network might only be trimmed every 5 years. But there are companies that are looking to optimize this process by using technology and digital tools to facilitate data-driven decision-making. So some of these solutions can use satellite or LiDAR imagery to enable what's called condition-based pruning. So instead of trimming a section of the network every 5 years, imagery that's collected can be combined with AI to identify where trees are actually encroaching on the network. So this information, this improved visibility, allows utilities to prioritize which sections of the grid should be trimmed in a given year. It can also help to reduce contractor costs because when the utility has better information about the amount of work that's going to be required, they can kind of sense check quotes and make sure that contractors aren't charging them more than the cost of getting the work done. So the result here is a reduction in operational expenses, which could instead be invested in network upgrades to support decarbonization. Reliability is also improved because the utility has better information about which trees are most likely to come into contact with the network. So they're able to take proactive measures to prevent that. And then the solution also promotes affordability because the cost to achieve the same outcome is lower. And to me, it's these types of solutions that are the future of electricity. Okay, so the first part of affordability is identifying opportunities for the utility to reduce their costs by doing work more efficiently. The second part of affordability, I think, comes from special programs and initiatives and incentives. So I had a hard time finding statewide data about energy costs, but the New York City Mayor's Office published this study in 2019, which I want to talk about for a moment. So this study looked at energy costs in the city to understand what percentage of families are considered to be energy burdened. So New York State in 2016 set a target that low-income families should be paying no more than 6% of their income towards energy bills. Otherwise, they're considered energy burdened. And so while recognizing that New York City has some of the highest energy costs in the country, the study still found that 14% of families with incomes less than 200% of the federal poverty level were considered to be energy burdened. And then looking at all families in New York City, 18% were considered to be energy burdened in 2019. This chart is a little bit hard to digest, but basically the bigger the circle, the greater the number of families that are falling below that 200% of the federal poverty level threshold. And then the darker the circle, the higher the annual bill. And the reason that I bring this up is because there are a lot of conversations right now about rising prices. And I think it's important to talk about, or important to recognize that when we're looking at affordability in the sense of the energy trilemma, we're really talking about access to electricity. So everyone wants to be able to come home from work in the evening and turn on their lights to be able to cook dinner. For families that have children, they want light to be able to do their homework. They want to be able to plug in phones and laptops. So this is what we're talking about when we look at, access to affordable electricity. So there are a couple ways that utilities are addressing affordability for low-income customers, as well as incentivizing adoption of clean energy technology. So utilities in the state administer the Energy Affordability Program, which provides income-eligible customers with discounts on their monthly bills. So this is a program that helps to ensure that low-income customers are not energy burdened. Empower Plus is a program that utilities are able to offer through a partnership with NYSERDA. This is again targeted at low-income and income-eligible customers. And if they apply and are approved, they're then paired with a participating contractor who will then complete a home energy assessment at no cost to the customer. They're also then able to receive energy efficiency improvements at no cost. And then the Inflation Reduction Act also made funding available to install heat pumps for these qualifying customers. The New York State Clean Heat Program allows utilities to offer incentives for customers to install heat pumps. So this one doesn't have, I don't think, an income eligibility requirement. And then incentives for this program are calculated based on the heat pump system capacity, but on average look to be a couple $1,000s. And this incentive is intended to support the state's building decarbonization goals and make clean energy technology more accessible. The EV Make Ready program was designed to support the CLCPA goal to increase the number of electric vehicles in the state. So through this program, utilities can provide incentives for commercial customers that are looking to install EV charging stations at offices, retail stores, apartment buildings, or other public destinations. And this program will fund up to 100% of the electric infrastructure costs that are associated with installing the charging stations. So the customer that's applying still has to pay for the charging stations themselves and the install, but the utility will fund any upgrades to the grid and interconnection costs. So now we've talked about all three components of the energy trilemma. State decarbonization targets are dependent on the fast interconnection of renewable energy resources in order to meet growing demand from customers. But as we interconnect more renewable energy to the grid, we have to ensure that reliability is not being jeopardized, so keeping that balance of supply and demand. We can leverage grid enhancing technologies like advanced conductors and dynamic line rating to increase the capacity of the transmission grid. We can also enhance the reliability of the distribution grid using FLISR and AMI to reduce both the number of customers that are impacted by an outage as well as the time to restoration. And then while conducting this pretty extensive grid build out, we also have to maintain affordability. So we can look to a combination of process improvements, digital tools, and improved data visibility to drive operational and capital efficiencies for utility, which helps to keep costs reasonable. Utilities can also offer targeted programs to ensure that low-income customers are not energy burdened, and they can also incentivize adoption of clean energy technologies. So, as this presentation has hopefully made clear, there is no silver bullet. There's not one solution that can address all of these challenges. As a society, we've been reliant on fossil fuels to generate electricity for over a century, so the transition isn't going to happen overnight. A comprehensive utility strategy to addressing the clean energy transition requires innovative solutions because these are complex problems. There are also trade-offs that have to be taken into consideration. We can't sacrifice reliability or affordability to achieve sustainability. But at the same time, addressing climate change requires rapid action. So I think this is a really exciting time to be working in the energy industry. This is what I think about and talk about all day. So I really appreciate your attention. Thank you again, Dr. Shankar, for inviting me to present. And I'm happy to answer any questions that you all might have.
Oh, wonderful. Thank you, Laura. As I mentioned in the beginning, I'd like to have the students ask first a few questions, and then we go to the general audience. Now, the two ways of asking questions: unmute yourself, introduce yourself, and ask them verbally, or you can, drop your question on the chat line, and between Susan and I, we will kind of go through all the questions. So thank you again, Laura. It's an excellent presentation. Okay, so if you don't mind not sharing, Laura, you can get all the people on the screen.
Of course.
Okay, good. All right. Questions for Laura from students first.
I have a question.
Answer, go ahead.
Hi, my name is Sajjad Al-Shimari.
Sorry.
I'm a student in ESE. Thanks for your presentation. It's very good. Just only I have a question about the wind. They will be, most of them, it will be onshore or offshore wind turbine. And the second question about the transmission line. There will be more just only overhead line or underground cable? Thank you.
Yeah, of course. So I think the first question was about wind power. So as far as the mix of offshore versus onshore wind in the interconnection queue right now, I'm not sure. New York State's target for offshore wind is 9 gigawatts. I know there have been some challenges with offshore wind recently. NYSERDA, I think, held a series of auctions, basically soliciting bids for offshore wind projects. And I think some of the developers that won those bids have since dropped out and said, we're not able to, complete this project at the cost that we originally bid in. So I think there have been some hiccups there. So yeah, I guess not super able to answer the question as to what there's more of in the queue, but I know there have been some challenges with offshore wind recently. So if you remember on the chart, we're lagging on that goal pretty significantly right now. And I think your second question was about overhead versus underground transmission lines. I think generally, a lot of the transmission projects that I hear about being built are overhead lines still. But for offshore wind projects, there are companies looking at doing undersea interconnections. So those will be undersea transmission cables. So again, I'm not sure what the majority there is. I think some of both. Thanks for your question.
Thanks, Paul.
Students, a question, please unmute yourself.
Yep. Hi. Yeah. Hi, I'm Spencer. I'm an undergraduate student studying physics and economics. And I was wondering about the rate structures because in one of my classes we talk about how the the return on investment for capital, that rate structure causes some issues, not really addressing some issues with the operating expenditures or not spending as much on operating expenditures, such as trimming trees. So is there a push to change that rate structure in the future?
Yeah, so I don't know that there's necessarily a push by a regulatory body or by utilities to change that rate structure. So I can talk about what I do know. In New York, a couple years ago now, Reforming the Energy Vision was the name of the program, and it added incentives for utilities to invest in non-wires alternatives. So I think part of the challenge that comes with utility profit being based on capital investment is that utilities might just build as much as they can, and they might build unnecessarily because they're getting return on that investment plus that return on equity. So the incentives in they're called, I think, earnings adjustment mechanisms in REV added incentives for utilities where if they invested in non-wires alternatives, so this can be things like demand response projects or batteries to defer, building a new substation, there's still an opportunity for them to earn there. So by investing in a lower cost system upgrade, they were still earning a return. They were getting that incentive. So I think that's one way that we can try to incentivize utilities with policy to do something different. But yeah, as far as large scale move away from the current rate structure, I haven't heard of anything.
Thank you.
Thank you. Questions for Laura? Students? Students? Questions? All right, so I'll open the floor for questions from the general audience, and I'll also go through some of the chat box questions. So if there's a lull in the action, I'll pick up the chat box.
Rudy, this is Jim Robinson. You might want to read my question from the chat box regarding dynamic ratings. I can discuss a study that was done by PPL, Pennsylvania Power and Light Company at the time, and PJM about 20 years ago, But go ahead, read the question I have in the chat box.
Yeah, do you want me to read it out loud, Dr. Shankar?
Go ahead.
Yeah, so question for dynamic line ratings, real-time normal ratings can be used. However, is a reliable emergency rating for our duration determined? Single contingency compliance requires a predictable rating for the next 4 hours during emergency generation redispatch. Do you mind elaborating on that a little bit for me?
Yeah, what this gets to is there have been dynamic line rating studies previously, and there are exotic conductors that can operate higher than 125 degrees centigrade. And PJM has used real-time temperature ratings based on temperature for the next 4 hours or so. But there was a study done about 20 years ago on dynamic line ratings for contingency analysis use by the operating department, which usually determine how much power flow can go across the network. If a single contingency occurs, you must stay within the emergency line rating at all times. The dilemma is the emergency rating, at least in PJM, its duration is about 4 hours. It can be significantly higher rating than the normal rating, but it has to be a predictable 4-hour duration rating. And back 20 years ago, there was a gentleman by the name of Septempa. His company installed tension sensors in the conductor on tension towers. We have two types of towers: suspension, where the conductor hangs from the tower, and suspension tension, where the tension for angles, where the line turns at an angle. He installed tension sensors that transmitted to PPL using a radio transmitter. So he knew what the tension on the conductor was at all time, and he predicted the dynamic line ratings. That worked quite well. Solar powered and did not require LiDAR. But the project ultimately failed the PJM 4-hour test for emergency rating. We could not at PPL, when I was there, come up with a 4-hour emergency rating based on the dynamic ratings that change moment by moment. We couldn't predict what the rating would be for the next 4 hours during generation redispatch. So I'm asking the question, have the new dynamic rating studies that you've seen include this issue of emergency rating, and how do you predict it when it has to be a reliable rating for 4 hours or so?
Yeah, that's a good question, and I appreciate all of that additional context. To be honest, I'm not sure that I know enough to be able to answer it. I'm familiar with, dynamic line rating technology and generally what the capabilities are. But as far as, what happens with emergency ratings and does the rating default back to like a static line rating or that seasonally adjusted rating? I'm not sure, to be completely honest with you.
Okay, the only thing I would suggest is any study of dynamic line ratings try to answer that question for New York ISO use and their emergency ratings, PJM emergency ratings. It has to pass those reliability bodies questions regarding making sure the ratings are reliable.
Yeah, my assumption would be that there is some sort of, process or mechanism in place. I would assume that the utility wouldn't be permitted to install dynamic line rating technology unless it was able to be compliant with the ISO and any applicable FERC requirements. So I'm sure that I'm sure somebody has thought about this, but I'm not sure what the answer there is, but appreciate the question.
Thank you.
All right, thank you. So let me just rattle off a question in the chat box. What impact do your studies show might occur because of the proposed tariffs on Canadian export of electricity from Hydro-Quebec?
Yeah, so again, this is something that I am aware of is happening. But I think as far as the specific impact, I don't know if there's a contract with Hydro-Quebec or if they're bidding into the wholesale market. Either way, I think the cost of hydro will increase if they're bidding into the wholesale market. I think that might impact, costs and, the order in which, generators are meeting demand, what the clearing price is. But yeah, I haven't read anything specific about that question yet.
That was a question from DC. I want to acknowledge. Anyone else with a question? Sorry.
May I ask a question?
Sure, Alberto, go ahead.
So, Laura, thank you so much for the presentation. Super. You covered a lot of topics, so it was very interesting. I had one clarifying question in the graph where you were showing the dispatch of the different generators, in which you showed that nuclear is completely flat. This is because they're not allowed to ramp, or because whenever they submit, they're not they want to maximize their energy income, and they're not interested in the ancillary services, or do you have an idea why that may be the case?
Yeah, so my understanding is that it's most efficient for nuclear plants to run at a pretty high capacity and consistently. So I think the economics actually get worse for the plant if they're kind of ramping up and down. So I think that's the primary driver there.
So it is a supply choice.
I think so, yes.
And on the demand side, I was interested, so there's been discussions for the last couple of years about the implementation of FERC 2222, which is much more about distributed energy resources, right? So how are they going to be entering into the system? I don't know if this is something that you have been discussing, but could you let us know a little bit about the discussion nowadays in terms of how are these energy resources going to be integrated? How more demand flexibility is going to be added into the system?
Yeah, that's a good question. This is also a topic that I'm not as familiar with. I think my team specifically has been talking a lot about for 2023 because we've been understanding what the cluster study process looks like in New York, kind of doing the first batch, but not as familiar with flexibility of distributed energy resources. And you said FERC Order 2022.
Right. Well, thank you so much, Laura.
Yeah, thank you.
Yeah,
I appreciate all the good questions. Unfortunately, I'm not a subject matter expert in many of these areas. So,
yeah, regarding FERC 2222, I know PJM has gotten some guidelines there as to what can we operate on the grid. But this is fairly new stuff, so let's see how things go. Proceed.
Yeah, there seems to be a lot of there's still, I don't understand that there's a settled debate, but it's there's a number of proposals out on the floor. So,
any questions from the general audience? Anybody unmute yourself, introduce yourself, ask the question, please. While you're thinking, Nate Nichols asked, shouldn't prearranged outages be removed from reliability metrics?
Another interesting question. I think I can give you my thoughts or my opinion here. That's still, time that customers on the system are without power. So I think incorporating pre-planned outages in reliability metrics probably helps to ensure that utilities are being intentional about when those outages are, how long they are, how many customers they're impacting. Because like power out is power out. Sometimes you need to do maintenance on the system, but somebody's still without power for a little bit. So that would be my thought there. I think it probably helps to just keep utilities accountable.
Another question: how widespread are AMI meters in New York? Is it 100% penetration?
Another good question. I'm not sure what the number is across New York. In National Grid territory right now in upstate, I think we're a little under 18% maybe. So we're still in the process of rolling out this newest generation of smart meters. But I think other utilities in the state have a prior iteration of smart meters potentially already installed. So I think most customers probably have some type of smart meter. As far as the rollout of AMI 2.0, I think it's just a little under 20% right now.
Good. Another question in the chat box. Is the Inflation Reduction Act funding for the heat pumps still in place in New York?
I am not sure. So I think there have been like impacts to federal funding recently. I think some of the funding in the Inflation Reduction Act was, I forget what the exact word is, but it had been like delegated already, like, and had gone to fund certain projects, had been, promised to fund certain programs. So I'm not sure if the heat pump funding is one of those qualifying items that was, promised and part of a prior budget, and so people get that money no matter what.
Oh, by the way, we'll have Jigar Shah present at the very tail end of our semester. So that's on April 21st. So keep that in mind. So you can have him, ask him a lot of questions about these big projects under the, how are they doing in this new administration? How do you think
the person to ask, right?
How do you think the current political climate around energy will affect these efforts? Well, this is a good question.
Yeah, I mean, I think that's the question, right? Again, I can give you my thoughts and opinion. As to this question, I think at the state level, New York has set very ambitious climate goals. Even though, we're not expecting to meet some of those goals on time necessarily, I don't think that the state has any intention of backing down from those goals. They were signed into law, so those are the goals, and I think they're going to stand. So at least within the state, there's still pretty heavy pressure to decarbonize and interconnect energy. I think the other important part of this conversation, like I mentioned with the EV examples, policy is one thing, customer behavior is another. I feel like every time I watch TV recently, there's an EV commercial for a new company that has come out with a new EV model. So at a certain point, the government stops driving progress as much as consumer demand does. So if more people keep buying EVs in New York, they're going to want charging infrastructure. So there's going to be that demand in the market. Utilities are going to have to build and service that EV infrastructure, and then do all of the other things that come along with supporting that growth and demand. So I think I try to remain relatively optimistic. I kind of am in the New York bubble, which helps. But I think we're starting to reach a point where, there's enough demand in the market that's driving progress. And so we're less reliant on like huge federal and state level incentives. So that's of course my opinion, but I think that's where we stand.
Question from M.Eng. He just says, I have a question. So M.Eng, M.A., please articulate what your question is.
Okay, thank you for your chance. Unfortunately, I'm out of the US and I'm from Ethiopia, and I think I passed some part of the presentation. And my question was lay on how can we balance decarbonization? Can you hear me?
Yeah, I can hear you.
Can you hear myself?
Yeah.
Okay, my question is how can we balance decarbonization target with energy affordability and grid reliability in terms of utility costs? How can we balance decarbonization with grid reliability with affordable energy sources, especially in green energy systems? That's my question.
Yeah, so I think as I discussed, there's no silver bullet, there's no one right answer here. The energy trilemma is a named problem because it's a really complex problem that's going to require a lot of different people working on it, developing innovative solutions and collaborating and doing hard things. So I think from my presentation, the gist of what I was hoping that you would get is that technology and innovation can be solutions that help to tackle maybe 2 out of 3 things at one time. There are always going to be trade-offs because new technology has an associated cost. So, depending on what the specific goal in the moment is, like you might not be able to hit all 3. You might have to make some trade-offs, but usually you can hit 2 out of 3. And then you might have to, find a different way to, address sustainability if you're focused on reliability and affordability, or you might have to apply for a grant to address the affordability aspect if you find a solution that can address sustainability and reliability. So I think innovation largely, and then just recognizing that there are always going to be trade-offs.
Okay, thank you.
Thank you, Bratu, and I'll look forward to seeing you in the fall semester. Questions for Laura? I just want to pass on a comment from Susan. I think this is Susan Blatt. She states that DLRs are being used, but largely for economic reasons, not for reliability. That's a good observation. Questions for Laura?
I think you still have a bunch in the chat, Rudy.
All of them.
Let me see. Did Jay Mehta's question get answered? He asked. Oh, yeah. He did. Okay. Blair Walters.
Yeah, that was answered too.
Okay. I'm just double checking.
Okay. If there are no more questions, I'll wait for a couple of minutes.
Yeah, thank you so much again. I appreciate the challenging questions. Definitely was taking notes and look forward to learning more.
Good. Well, thank you again, Laura. I know that you were in the middle of a lot of things for your utility, and thank you for accommodating us for today. And we look forward to another seminar, another semester. But best of luck. And thank you all, the audience. And we will be having another presentation from EPRI 2 weeks from now, March 17th. It's in the practical realities of the energy transition. So make sure you register for that, and we'll see you then. Thank you all.
Thank you.
Thank you.
Thank you.
Thanks, everyone.
Thank you. Welcome.